How hard can we pull on that cord before motion occurs? We have 3 separate blocks here, and there's a coefficient of friction between all of those interfacing surfaces, and each block has a different weight as well. So they tell us that the blocks are 50, 25, and 15 pounds. And the coefficients of friction between each of the surfaces, so AB is 0.3, BC is 0.4, and between C and the ground is 0.35. So we want to first think, how can these different objects move, since there are multiple objects in this one? And then that will later tell us what are the types of equations we're going to need motion-wise to test the different ways that motion could occur. So how could motion possibly occur in this problem? B kind of slips out between A and C would be one way it could move. B and C stuck together, slide relative to the ground, slide relative to A. And in this problem, we're not told any of the dimensions about the height or the lengths or about are the blocks homogeneous. So in this case, we can't test for tipping. We don't have enough information here. So we're only going to consider slipping in this particular problem. If I told you the heights and the widths, and if, say, the weight acted in the center, then we would have enough. So in this example, there's only 2 ways that our system can move. B slides alone, or B and C together are going to slide out from under this. A is not going to be able to slide relative to B because it's tethered to the wall, and since we're pulling to the right, we would not expect A to be able to move to the left. So 2 motion scenarios that we want to consider here, and we have 3 blocks. All right, let's look at the free body diagrams first for each of our pictures. On each block, they're all going to be impacted by their own weight. So I can start there. Block A was the 50 pounds. Block B is the 25. And block C is the 15. On block B, we have the applied load to the right of P. And on block A, we'll have the tension to the left, which we don't know what its value is right now. Now we have to think about those contacting forces between the surfaces. There's going to be the contact or the normal force between each one, and they all are going to be impacted by friction also. I'll start with the normal forces. So on block A, there's going to be a normal force that prevents it from falling down because it could only move left-right. So there's going to be a normal force between block A and block B. I called that NA in my picture. Don't presume, it does turn out to be 50 pounds, but don't presume it's equal to the weight force. Let the math tell you that that's correct. Again, I don't necessarily know where it's located, but in this problem it won't matter because I'm not going to be checking for tipping. But if I were checking for tipping, I'd have to put this some distance from a corner that I'm thinking it might pivot about. So that's the normal force that's acting on A. Because these 2 A and B's are in contact with each other, the normal force that's up in this picture is going to be down in this picture. So I have the normal force A down in my picture B, equal and opposite at the same location. But on B, it wants to fall down due to gravity, but block C is going to push it back up. So there's another different normal force between surface B and C that I'll call NB. And then on block C, we'll have that equal and opposite normal force coming down from B. And preventing C from falling to the center of the Earth is the ground. So there's another different normal force there that I'll call NC. And I'm not modeling the ground in this case. So as far as the normal forces go, that's all of them. Normal forces can only push, so I know that these are the right directions for my normal force. There's also friction between all of my surfaces that I have to model, and this is where the direction is going to be maybe not as obvious. So if we start with a block that we know what's happening with, that's going to be a better case. So I'll actually suggest starting with B when we're modeling the friction here. We know that friction always opposes the motion, and really to specify, it's the relative motion between our surfaces. So for block B, how do we presume that block B is going to be moving with at least respect to the ground? Right, we think it's going right, and one of our scenarios was that it slips out between A and C. So it would be moving to the right with respect to A, which can't move, and it would be moving with respect to C, potentially, if it could just slip out there. So if its motion is to the right, then we'll have a friction force at the top and the bottom that both are opposing that relative motion. So again, we think it's going to move relative to C, to the right, and relative to A to the right also. So this friction at the top, that I'll call FA, and a different one on the bottom, FB. Because I already decided the directions of the frictions here, that means it's also decided then on the linked blocks. So if FA was to the left here, it has to be to the right in picture 1. Again, relative to block B, block A is slipping to the left. That's why FA is pointing to the right. Again, it's relative motion of the surfaces, not absolute motion with respect to the ground necessarily. Because I said FB was to the left in this picture, then FB must be to the right in picture C. And finally, in picture C, the other movement scenario we said was possibly B and C are stuck together and move to the right. So relative to the ground, in picture C, I'll also have a friction force to the left. Because relative to the ground, it would be moving to the right. Let's start with the equilibrium equation, since that's the more straightforward part here. If I sum my forces in the x direction in picture A, I'll get negative T plus FA. So the force of friction A is equal to the tension in the rope at equilibrium. In the y, I get negative 50 plus NA. So here we do see that that first normal force is equal to the weight. In picture B, in the x direction, we'll have minus FA minus FB plus P. And here in the y direction, we have the normal force of A down and the weight down, the normal force of B up. So NB is the weight of A plus the weight of B. And in the x direction in picture C, we'll have minus FC plus FB. So at equilibrium, those two frictions have to be equal. And in the y direction in C, I'll have minus NB minus the 15 pounds plus NC. So that normal force C is 90 pounds. So yeah, I only get those 6 equations out of this. I can't take any moment equations because I don't know the distances of anything. But I have 6 equations for those 8 unknowns. So the extra equations are going to come from how is motion going to occur, or how possibly can motion occur in this system. We discussed at the top 2 different ways we could think about for motion to occur in this system. Either block B will slip out between A and C, or B and C will stick together and then slide together relative to the ground and relative to A. So each of those is going to present us with a different set of at least 2 more equations that we have to figure out. So I'll just say that condition A will be that block B slides relative to A and C. Right, so it slips out from the middle. So what has to be true if block B is sliding relative to A and relative to C? That means that the friction force between A and B, between those 2 contacting surfaces, must be at its maximum value. So it's just about to slide relative to each other. So FA is maxed out, so that's the coefficient of friction between those 2 surfaces times the normal force between those 2 surfaces. And we were told mu AB was 0.3, and NA we found out to be 50 pounds. We've introduced a 7th equation and no more new unknowns, but now we have 7 equations for our 8 unknowns. But motion-wise, what else has to be true for block B to just be about to slide out from between A and C? Simultaneously, also, the friction force between these two surfaces has to be at its maximum, because we can't slide relative to one without sliding relative to the other one under this condition. So we couldn't be sliding with relative to A, but not with C. That was actually our second condition where those slide together. So also at the same time, what I called FB is at its maximum. So I used 0.4 times normal force B, which was 75. Between equations 1 to 6, 7a and 8a, now I have 8 equations for my 8 unknowns. And now it's a solvable system because of that. So solving these, I now know for condition A to happen what the value of FA is and what the value of FB is, since they're both at their maximum values. So solving this all simultaneously, since I know FA from 7a, I know FB from 8b, I can use equation 3 to find the value of P that would cause this. So here, for condition A, force P would have to be 45 pounds. That's what it would take for B to slip out relative to A and C. But we don't know that's necessarily what's going to happen. We also have to check, kind of our alternate theory, is that B and C slide together relative to A and the ground. Right, so they stick together and slide together, which means we'll have 1 to 6 are still true since we're still talking about being on the verge of slipping, but we need a new 7 and a new 8. Right, so in this condition, what is going to have to be true if we're just on the verge of slipping now relative to the ground with C and relative to A with block B? 7A and 7B are actually the same because we're still saying that B and A are just about to slide relative to each other. So 7B must be the same thing. FA is 0.3 times 50. In this case, because we're saying in this scenario B and C are stuck together, we're not saying that the B and C surfaces are just about to slip because they're not slipping relative to each other is what we're saying. But C has to be slipping relative to the ground or just on the verge of it. So FC is maximized, and that's going to be the 0.35 times the normal force between the ground and C, which was 90. We have now these 6 equations, and then plus these 2 equations. 7b is actually the same as 7a was, but this is different here. I know that FC is equal to FB, so I can use that information. And again, I know negative FA minus FB plus P must equal 0. So solving these simultaneously, I get that the force I would have to exert, 46.5 pounds. These were the only 2 scenarios we had to consider. This takes more force than it does for condition A to happen. So by the time we could pull with 46.5 pounds of force, block B would already be sliding out relative to A and C. So this is what's going to happen first. We can apply up to 45 pounds